Okay, guess we can start. Good morning, everyone, and welcome to the first session of the last day of Eurocrypt 23. This session will be on signature schemes, and in particular on signature schemes for privacy-preserving applications. So we have three interesting talks. The first talk is Revisiting BBS Signatures. It's a paper by Stefano Tesaro and Chenqi Chu, and Chenqi will give the talk. The stage is yours.
Hello, everyone. Thank you for the introduction. Today I'm going to talk about our work on BBS signatures. It's a joint work with my advisor, Stefano Tesaro. So BBS signature is a parent-based scheme, and we should know that it is not a BBS group signatures. So for the setup, given a pairing description where P denotes the group size and E is a pairing, we sample two generators, G1, H1 of a group of the group 1 and of generator G2 of group 2. And for key generation, we sample random X, and the secret key is X, and public key is G2 to the X. And for signed message M, we first sample random E, and then we compute A as follows. And the final signature is just E and A. And to verify a signature is valid if and only if this A to the X plus E is equal to G1 times the H1 to the M. So if with pairing, we can efficiently verify with a public key as follows. So we can also extend the message to be a vector in ZP. And also, BBS can be instantiated from the type 3 pairings, which allows for the most efficient implementation, such as the BLS12 curves. So one significant application of BBS is in the construction of anonymous credential schemes. So in such a scheme, the users seek to obtain credentials for some attributes M from trusted authorities, referred to as the issuer, such that the credential can later be shown to others in an anonymous way. So BBS can be used as a credential, and later when the user wants to show the credential for an attribute, but without revealing the credentials, the user can send the attributes to the verifier together with a zero-knowledge proof of knowledge of the credential. And the user can even review only certain parts of the attributes using zero-knowledge proof. And another related use case of BBS is in the construction of direct anonymous attestation schemes. So the history of BBS signature is a bit complicated. So BBS signatures was implicitly proposed by Bonnet, Boyan, and Sachin and as part of their group signatures. And then it made explicit by Kamenis and Lizanskaya in 2004, but without a security proof. And then in 2006, a variant called BBS Plus was proposed, and with a security proof in the setting of type 2 pairings. So the difference between BBS Plus and BBS only lies in the additional S value sampled during each signing. And this S was, so it contributes to an extra terms when computing the A, and is also added to the signature. And then in 2010, DA schemes from BBS was proposed, but its security proofs turned out to be incorrect. So if the proof is correct, it will imply the security of BBS. And then in 2016, a DAA scheme from BBS Plus was proposed, and together with a new proof in the setting of type 3 pairings. And also quite recently, there's an ongoing standardization efforts for BBS Plus by the WC 3C and RFC. So if you see the history, a natural question to ask is whether BBS signatures are provably secure. So in this work, we give affirmative answer to this question, and more precisely, we show that BBS is as secure as BBS Plus. So the security proof we give support the type 3 pairings, and also it provides the same security levels as prior proof for BBS Plus. So BBS is just more efficient. And also this work also provides a potential fix to the prior incorrect proofs which implies a secure DAA scheme from BBS. And furthermore, we also accompany our standard model proof with a tied AGM proofs, which enabling more efficient parameter settings when in the practical use of BBS. We also introduce a more efficient POK for BBS. And lastly, we also analyze the blind issuings of BBS signatures. I will also like to highlight there's an ongoing efforts to adapt RSA draft for the BBS and our POK protocol. So before diving into the technical parts, I would like to give you an overview of how the improvement we have made to this POK protocol. So here is the best POK protocol for BBS Plus prior to our work, and it was adapted by the RSA draft. And here's this work. So you can see that the scheme is much simpler, and concretely it saves one group elements plus two scalars in the size of proof. And if we instantiate using this BOS 12381 curves, it saves about 900 bits. So for the rest of talk, I will focus on how to prove BBS secure. So here's a prior theorem for the security of BBS Plus, so which shows that BBS Plus is strong and fungible. We're reducing it to a Q-strong Diffie-Hellman assumption. So we are here, the Q will represent the numbers of signing queries. So an assumption is defined using the following game, where initially two group generator was sampled together with a challenge. And the adversary is given G1 and G1 to the X, and all the way to the G1 to the X to the Q, and together with G2 and G2 to the X. And the goal of the adversary is to output a C and Z, such that Z is equal to G1 to the power of 1 over X plus C. And so here is the theorem we proved. So we proved exactly the same theorem, but for the BBS. And also we have proved a tight AGM bound for, and we have also prove a tight AGM bound. However, in this talk, I will mainly focus on the standard model proof. So let's start by recording the strong unforgeability game. So initially, the challenger will generate all the generators and also secret key, and then assign the generators and the corresponding public key to the adversary. An adversary have access to a signing oracle, which signs we can sign any given message. And here we index the signing queries by I, where I is bounded by Q. And the goal of the adversary is to forge a message and signature pair that are valid, but is different from all rows that are generated by the signing oracle. And now we can turn our attention to the task of constructing B that breaks the Q-strong Diffie-Hellman assumption. So the relation here is that if A wins, there are three cases. So the first one is when the E star is not equal to any one of the E value. And the second case is the E star is equal to one of the E value, but AI is not equal to A star. And if the above two cases do not occur, we have there exists an I such that the E star and A star is equal to EI and AI. It turned out that the case 1 and case 3, we can handle it using the prior techniques. But well, the case 2 proposed the greatest challenge, and we have need new techniques to address it. And in the following discussion, I will develop into each of the three cases. So for case 3, it is easy to see that it never occurs. Okay, so if suppose case 3 occurs, then we have the following equation. And then we can find it implies that this mi's will be equal to m star, which contradict with the winning condition of A. And in general, this case 3 occurs if the m is a vector, but then it will break the binding property of Patterson commitment. And then for case 1, we can select B as follows. So the B was first sample all the e-values that are used in the signing oracle at once. And without loss of generality, we assume that all the e are distinct. And then we define the polynomial p as the product of x plus ei. And then b runs a by with the generator g1 bar and h1, which are computed as follows. So here the theta and alpha random factors. And then I see that this g1 bar can be efficiently computed because its degree of p is only q. So we can compute it using the inputs of b. And then we need to simulate all the signing queries. So for the I signing queries, the b need to compute this AI, basically. And you can see that this AI can be represented in this form. And because this px is divisible by the x plus ei, so b can compute this AI efficiently. And then if A wins, we can represent this A star as the following. And then because this P is not divisible by X plus E star, since the E star is not in the E, it's not equal to any one of the EI. And then we can use a class of techniques from Bonnet and Boyan to compute the G1 to the 1 over X plus E star. But however, this method does not work for the case 2 because the E star is equal to 1 of the EI. And before we discuss our solution, I would like to first review how the prior works handle it for BBS+. So the idea is that the B is going to sample so guess an I star, such that the EI stars collide with the value of E star. And then we simulate the I stars queries differently. So here the reduction is a bit complicated, and I would not dive into the computational details, but just highlights a few key points. So here we define a new polynomial, p prime, which is actually equal to p divided by x plus ei star. And then we generate this G1 bar exactly the same as case 1, but with this p prime polynomial. As a result, we find we can simulate all the signing queries for I that is not equal to I star, the same as case 1. But then the question is how we simulate the I stars query. And to simulate it, you need to compute this AI star. And so we're doing it by trying to first represent it by in the base of G1. So given how the generators are computed, we can actually compute AI star in this form. And so from there, you can see that if this highlighted part is 0, then we get these two terms of x plus ei star which get canceled. And therefore, this AI can be efficiently computed. So, and thus, we just need to set this SI star to alpha minus beta times mi star. And then the next question is how to extract a valid output. So suppose case 2 occurs, and we have E star is equal to ei star. And then similarly, we write down this A star in the base of G1. And now we're trying to show that this highlighted part is not equal to E star. Sorry, it's not equal to 0. And so case 2 occurs, we can finally show that this inequality, which is the beta m star plus s star, is not equal to beta m I star plus s I star. So, and then during the reduction, we have this equation, which is the alpha minus the left-hand side of the equation is equal to 0. And therefore, we have the alpha minus the right-hand side of this equation is not equal to 0. As a result, we can see this polynomial in blue is not divisible by the x plus e star. And therefore, we can compute this G1 to the 1 over x plus e star the same as using the same technique mentioned in the case 1. So then we're ready to explain how the idea is to get rid of this SI. So in the previous proof, the role of SI is critical because the SI need to make sure this highlighted part is equal to 0 for any MI chosen by the adversary. Another idea here is to use this EI star to play the role of this SI star. And this is actually possible because this EI star does not need to be terming at the beginning. So more precisely in our reduction, the B does not sample EI star at the beginning, but instead it samples another randomization factor epsilon. And then it's generate this generator as follows. And then we can see similarly that for any signing round for I is not equal to I star, we can simply do similar thing for case 1, simulate the signing queries. And then the question is first is how to simulate the I stars query, and then how to extract the valid output for this q-SDH. So for the first question, we do a similar thing, and we just represent this AI star in the base G1, and we'll see this. The B set this EI star to be this high lighted parts, and then this last two terms get cancelled, and therefore we can efficiently compute the AI star. And moreover, we have this EI star is uniformly random due to the randomness of epsilon. And then for the second question, we do the similar thing. We just represent AI star in the base of G1, and we're trying to show that this highlighted part is not equal to E star. And and then because case 2 doesn't happen, we have this M star is not equal to MI star, and therefore we can show this highlighted part is not equal to E star. And similarly, we can show this polynomial in blue box is not divisible by the X plus E star, so the B can compute and wins again. So finally, I want to briefly mention our analysis of blind issuing of BBS. The protocol works as follows. So the user first sends a Patterson commitment of the message to the issuer and receive the corresponding BBS signature in return. So our security objective here is to achieve one-more forgeability, which guarantees that the adversary cannot forge more valid signatures than the number of signing requested. And in this work, we show that the presented schemes achieves one-more forgeability in the algebraic group model. And finally, in conclusion, the main takeaway is that the BBS is provably secure as BBS plus, but more efficient. And for open problems, it's interesting to see whether we can do efficiency improvements using our results in applications of BBS plus, for example, for threshold signings. And that's all for the talk. Yeah, thank you. I'm happy to answer the questions.
Are there any questions? So if so, please come up to the mic. I think we have time for questions if there is anything. Okay, so then one question from my side. So you mentioned that there is industry interest on BBS plus, so there is RFC standardization efforts, and did I understand correctly that they already integrated your updates and now use BBS instead of BBS plus in the RFC?
Right. So they used BBS plus because they had no proof of BBS, and because of our proof, they trying to adapt the draft to use BBS and also our proof of knowledge protocol.
Okay, very nice.
Yeah, thank you.
And then thank you again. Okay, so the second talk in this session will be by Lucian Hanslick on non-interactive blind signatures for random messages.
So, sorry, thank you for the introduction. So today I would like to talk about non-interactive blind signatures, but first let's recall what actually two-move blind signatures are. So in the two-move setting, or in blind signatures in general, we have a user who we can also call a recipient and a signer. And the user wants to get his message signed without revealing it to the signer. So how do we usually do it? In two-move blind signatures, we have a requesting phase where the user puts in the message and the public key of the signer, creates a request, keeps some state locally, and sends this request over to the signer. The signer takes this request, creates a pre-signature using the secret key, and sends the pre-signature back to the user. So the user finally taking the pre-signature can obtain the final signature, but by applying the previous state that it kept locally on his machine. So what do we require from blind signatures is unforgeability for the signer. Basically, this means informally that whenever we want to receive a new signature on a message, we have to communicate with the signer. On the other hand, the user wants blindness, which means what it says. The message that the user wants to get signed should be hidden from the signer. Okay, so two-move blind signatures and blind signatures in general have a lot of applications. Today I would like to talk about one of the recent applications of blind signatures, which is Privacy Pass. And Privacy Pass tries to tackle the following problem. We have a browser and a content delivery server, and the user is trying to access this content delivery network using some anonymous network, right? So Tor or VPN, whatever. And the content delivery network is more prone to try the user and to give him more captchas to solve, because the user is using an anonymous network, so the web server is trying to protect against malicious actors. So users that are using anonymous networks have to solve more captchas, and Privacy Pass tries to solve this problem. So how Privacy Pass solves this problem is actually pretty simple. We have an additional party, which is the issuer. In our context, you can think about this as the blind signature signer, and the browser interacts with this issuer to get some blind signatures on random messages. You can see this message is chosen by the browser. And the key property here is that the browser can basically use a standard network to get those tokens, to get those signatures, and solves at the same time solving some captchas. And later on, it can use this message signature pair using the anonymous network to get and redeem this, redeem those tokens instead of solving the captchas when browsing anonymously. So from user perspective, it's a seamless process where you basically solve something at the beginning, and then when you are browsing anonymously, you don't have to solve anything. Everything is done in the background by your browser extension. Okay. So when you look at this in more details, the one thing that we have to keep in mind here is that the web server has to store this message to protect against double spending. So he has to keep a block list of messages, because this message is chosen by the user himself, right? So the user or the browser extension chooses this message. So the web server has to keep a list of those messages. But the nice thing is that this message doesn't need any kind of structure. It can be any arbitrary random string. So the question is, can we actually use this, right? Because this is very common in many, many applications of blind signatures where you don't care about the structure of the message. It can be any random string that the user just chooses arbitrarily from whatever distribution it wants. So can we leverage this, right? So let's try to define blind signatures for random messages. So again, we have this two-move setting. We discard the message, right, from the request, because we want the message to be random in the sense that it's an output of this finalization process. So when the user finalizes the message is basically a byproduct of finalizing the signature from the pre-signature. Okay, but this is not really interesting, because on one hand, the signer still has to use the request from the user, and the user has to keep a local state to finalize the signature. And what is more, we actually know how to build efficient two-move blind signatures, and Benedict will be talking about this in the next session from simple assumptions. So why do we limit ourselves to less features at the expense of something that isn't interesting, right? So the key idea here is that what if we replace this state that the user has to keep with a public key infrastructure, right? And this is how we go to non-interactive blind signatures. So now we assume that the user or the recipient has some key pair, right? So a secret key, public key pair. You can think about this. We have a preset PKI. So now the signer, instead of creating the pre-signature based on the request from a user, it basically creates this based on his public key. So the pre-signature and some nonce, we will get to the nonce later on, is sent over to the user, and the user just uses this, his secret key and the pre-signature it got from the signer to obtain the final message signature pair. And the key observation here is that the message is actually a function of the secret key and the nonce chosen by the signer. And why this is where the nonce comes in. So if this would be just the function of the secret key, you could only have one message based on one pre-signature. So this wouldn't be that interesting, right? So we will have one public key that could, so from one public key you could just get one message, but with this nonce we can actually have multiple pre-signatures per public key. So the signer can send multiple pre-signatures to the user, and the user can obtain many message signatures pairs. Okay? But of course, right, so we assume a PKI, how to use non-interactive blind signatures without a PKI. So the idea is that the user has this recipient key generation algorithm. In the previous case, we explicitly assumed that this is the PKI key generation algorithm. Here we say that he runs this rkeygen. It sends over the public key to the signer, right? And the signer can create a pre-signature and nonce. But that's basically two-move blind signatures, right? So nothing interesting here. But the clue observation here is that the signer can actually send over another pre-signature without contacting the user, right? The user can go offline, and the signer can basically create another pre-signature. It can even do it in batches. So you can think about, if you think about the privacy pass example, when the user wants more tokens to have spent against some captchas, he can basically send over just one message, which is the public key, and get a bunch of tokens in a batch. In comparison, for currently, you would basically have to send the number of requests the number of tokens you want to get. You would have to send the number of requests to the server. And the other nice feature is that like I said, the user can go offline. So we can think about the server doing the signing later on and just uploading this pre-signature on some server, so the user can just go there and download this pre-signature and finalize it locally afterwards. Okay? So let's talk a bit about security. I will not go into the detailed specification of the games, because in case of unforgeability, that's basically similar to standard blind signatures. We have the adversary is allowed to ask up to k times a signing oracle for pre-signatures. He can specify the recipient, he can specify the nonce, and gets pre-signatures. And his task is basically to create k+1 message signature pairs, which is similar to this one-time unforgeability of blind signatures. But the interesting part comes now, right? So in blind signatures, we just have one blindness definition. Of course, we have different variants, but it's just one blindness definition. Here, we need to distinguish two cases. One case is recipient blindness, and this basically means that when the signer sends pre-signatures to two different users, the final signature that it sees should be unlinkable to who was the original recipient of this pre-signature. So think about this, if I'm sending someone, two users different pre-signatures, when I see a final signature, I don't want to be able to tell which one was the one that created this final signature. So this is recipient blindness. And then we also have nonce blindness, which is also an interesting feature because it allows us to send more signatures to a specific user. So in this case, we have just one user, and we're sending two pre-signatures on different nonces to the user. And we then see one final signature, and we have to distinguish which nonce was actually used in the pre-signature for the final signature that we see. Okay, so that's with security. The interesting part is how to actually build this, right? So one of the building blocks, and the main building block for our efficient construction, for my efficient construction, is signatures on equivalence classes. If you know Daniel's work on this, that's actually a quite interesting privacy-preserving feature. So let's talk about equivalence classes first, right? So what is equivalence messages? So think about one message that, in this case, it's just a vector of two group elements, GA, GB. And we then have this additional message, which is m prime, and that's basically you take a random vector, random scalar r, and you exponentiate both group elements, and this creates our equivalence class. And what I mean by this equivalence class is that if you look at the discrete log between those two elements, it basically stays constant if you use just a randomizer, right? And this forms somewhat a class. Assuming the order is q, you basically have q classes and q elements in each class. And the nice feature for equivalence class signature is that if you unforgeability holds with respect to those classes. So basically, if you sign one of the classes, it's a signature for all the messages in this class, but you are unable to forge a signature on a different class. So basically, think about this. You have a signature on this vector, but you are unable to do a signature on GA GB plus 1. So when the discrete log changes, okay? But that's not really the most interesting part about this kind of signatures, because assume you have a signature on equivalence class signature on the message, you can actually adapt it without the secret key. This is important. Without the secret key, you can adapt it to a signature on this m prime, okay? And the nice thing is, like, once you adapt it, this new signature looks like a freshly signed signature. So even a malicious signer cannot distinguish whether you re-signed the message or it was adapted, okay? And this has a lot of interesting application. So if you want, read up on the work from Daniel. Okay, so how to construct efficiently, how to efficiently construct those non-interactive blind signatures, right? So what is the pre-signature? The pre-signature is very simple. It's just an equivalence class signature on the following vector. The first element is the public key of the user, of the recipient, right? And the second element of this vector is hash of nonce, where hash is basically hashing to the group. Okay? What is the message? The message is hash of nonce to the inverse of the secret key. And the final signature is just an adaptation of this pre-signature. And so basically, to adapt the signature, the user uses this inverse of the secret key. And what is going on there is basically that the final signature is a equivalence class signature on the vector where the first element is just a group generator and the second element is the message. So you can imagine verification is fairly simple, right? You just you construct, you take the message, you add the group generator at the beginning, you form a vector, and you apply the standard verification of equivalence class signatures. That's it. That's over. This is the construction. And the nice thing here is, right, I was talking about that once we have a PKI, it's non-interactive. And exactly in this construction, we can just use standard Diffie-Hellman keys for the group. A little caveat here, this is, so equivalence class signatures currently still need pairings, so the public key is an element of the source group in the pairing group, but that's something we try to solve. Okay, so why is this actually secure? So unforgeability is easy. It's just unforgeability from the underlying signature scheme. But the key observation here is that the message that you get is hash of the nonce to the inverse of the secret key, right? So if you look closely, this is basically a PRF for the recipient's key. And because of that, we can actually prove easily blindness. And blindness follows from the inverse and the strong decisional Diffie-Hellman assumption. Okay, so let me summarize what I actually did in the paper and try to formalize some open problems. So I introduced this notion of non-interactive blind signatures. I also proposed how to date non-interactive blind signatures. By dating, I'm not mean dating. I mean in the context of partially blind signatures, right? If you know, the idea is basically the signer can add a constant information that doesn't change after finalization. So you can think about this. For today, I will issue signatures with the current date, right? And this is the notion of tag-based non-interactive blind signatures. And the nice thing here is that the efficient construction that we had that I presented from signatures on equivalence classes, you can actually very easily transfer this to the tag-based setting, because we me and Daniel actually introduced the notion of tag-based equivalence class signatures. So you can just replace the building block and that's it. Okay, so if you remember this observation that the message is basically a PRF, right? From this observation, we were able to actually build a generic construction for non-interactive blind signatures. Of course, it's not a PRF, it's a VRF, but the idea is basically the signer signs the nonce and your public key, and what you prove is that the message that I show you is the evaluation of the nonce that's inside a signature I know for the public key, VRF key that's inside this signature that I know. So roughly, if you're interested, look it up in the paper. But the more interesting part are many open problems that we still have, right? So one of the key open problems is how to do it in the post-quantum setting. And why is this important? Because if we solve this, then we can do privacy passed post-quantumly, right? And this would be nice. Another thing is like how to do it without pairings. And this is what I mentioned, that the caveat for this construction is that that the recipient's public key has to be in the pairing group. So we don't really can use all the public keys that are out there, right? We would need a construction without pairings on standard curves to allow us to use every like ECDSA key, whatever, Schnorr key, whatever you want, right? So to use those public keys, we would need a construction without pairings. And the other interesting thing is how to do it without random oracles, because then we could answer some interesting theoretical questions, whether like blind signatures, if you just look at random messages, you can build them from simple assumptions without a CRS and random oracle, which is one of the impossibility results for blind signatures. Okay, so thank you for listening, and I'm open to questions.
Thanks a lot for the very nice talk. So are there any questions from the audience? Okay, so I have one question. So because I think I cannot really remember. So when you do the generic construction, like VRF and NISIC, so I mean there are elliptic curves VRFs, but they already need a NISIC for the verifiability, right? And then you would do a NISIC over a NISIC, and then okay, I see.
Okay. So basically the efficient construction would be nice to be without pairings, right? But of course, you could instantiate the generic construction without pairings, so then you could use this. But this is basically like you have to prove that whatever is inside a signature that you know has some kind of structure. So I think this might go in the direction of yeah.
Yeah, I see. Okay, thanks. Okay, if there is no more questions, then let's thank Lucian for the talk. Okay, so the last talk in this session is on blind signatures with pairings, I guess. And it's again by Lucian, by Julian Loss, and by Benedikt Wagner, and Benedikt is going to give the talk.
Yeah, thank you for the introduction. So this is about Raichu, a new blind signature scheme, and as said, this is joint work with Lucian, who gave the talk, and Julian, and yeah, myself. So I want to recall blind signatures first. We heard about them just a few minutes ago, but let's get everyone on the same page. So a blind signature scheme is a protocol where we have a user and a signer. The signer holds a secret key and the user holds a message. And now this message should be signed. For that, they interact in some protocol and the user outputs a signature. The property that makes it non-trivial is that you want blindness. So the signer should not learn what he is signing there. More precisely, he should not be able to link the interaction to the message signature pair. And then we also have this notion of unforgeability, which guarantees some security for the signer. The user should not be able to come up with signatures without interacting with the signer. So in other words, if you want L signatures, you need to interact L times with the signer and not less. Okay, so when it comes to constructing blind signatures, we mainly care about efficiency and security, as for any other cryptographic primitive. And in terms of security, of course, we want standard, well-studied, minimal assumptions that we are confident in. And we also want a property that you could call full security. So what I mean by that is that the scheme remains secure even if the adversary is allowed to talk to the signer an arbitrary polynomial number of times. Okay, now if we look at the state of the art, then unfortunately it is basically pick 2 of the 3 properties and you can't have more. So for example, there are schemes that are efficient, they come from standard assumptions such as D-log, but they don't have this feature that they allow for polynomial number of signatures. Probably the most promising step towards a scheme that has all 3 properties is a scheme from last year's crypto, where the scheme is not as efficient as we might hope for, and our goal in this work is to sort of fill this gap and have a scheme that has all 3 properties at the same time. And for that, we will follow this line of work that was initiated by Katz, Loss, and Rosenberg and try to improve the efficiency of it. Okay, so talking about efficiency, I should probably clarify what I mean by that when we talk about blind signatures. So of course, this is a signature variant, so we care about the signature size. We want compact signatures. And on the other hand, this is an interactive protocol, so we care about communication complexity. How many bits do I need to send back and forth to compute such a signature? And of course, we also care about computation. Okay, now that we know what we want, let me summarize some background of this work before I can actually present our result. So this is a line of work that was initiated by Katz, Loss, and Rosenberg, and I would call it the world of boosting. So what is boosting? It's a way to take a weakly secure blind signature scheme and turn it into a fully secure one. What do I mean by that? So Katz, Loss, and Rosenberg, they started with a logarithmically secure blind signature scheme. So the scheme is only secure as long as the adversary is allowed to talk to the signer only a logarithmic number of times. And we have efficient construction for that from standard assumptions. And now what they do is they transform this into a fully secure blind signature scheme in the sense that I mentioned before. You can have a polynomial number of interactions with the signer. Let's take a quick look at how this is done at a very high level. So we have the signer and the user, and now the first thing they do is they interact in n sessions of the underlying logarithmically secure scheme. But before they complete these sessions, the signer wants the user to convince him that he behaved honestly and followed the protocol, and for that they do a cut and choose kind of protocol. So the signer will pick one of these sessions at random and ask the user to open all other sessions by giving him the commitment, the randomness that he used to compute all his messages. And then the signer can check that he behaved honestly by recomputing everything. For the remaining session, they will finish it, and the user will then use this to come up with his blind signature. Okay, so that's the idea. Now the question is, how many of these sessions do you need? What is n? And in Katz, Loss, and Rosenberg's work, and also in follow-ups, n is a counter, so the signer has to keep a state, and whenever a user comes along and wants to get a blind signature, starts interacting, the signer will increase this counter, and this means that the number of sessions increases over time. Okay, so how does that look? If we look at all the interactions that this signer does with his public key, then in the first interaction, we will just have a 1 out of 2 cut and choose, then a 1 out of 3 cut and choose, and so on. So that's this idea of boosting. Now let's see why this helps us to get fully secure blind signatures. So we take the perspective of a reduction. In a reduction of the security of blind signatures, we need to simulate the signer. And now we can consider different cases. So let's say we have a malicious user interacting with the signer oracle, and this user malforms or is dishonest in more than one session. Then, of course, he has to open all but one of them. So that means he will be caught cheating, and That means we don't have to really simulate the signing process. Then there is, of course, the good case where the user is honest and does not malform any of the sessions. In this case, Katz, Loss, and Rosenberg showed by appropriately programming the random oracle, you can simulate this without using the secret key. Okay, the remaining case is actually the tricky case. What if the user malforms exactly one session? In this case, it could happen that we hit this session, and this is the random session that he does not have to open. We call this case a successful cheat, or a cheat for short. And in this case, actually the only way that we have to simulate the signer oracle is to rely on the signer oracle of our underlying scheme, of the logarithmically secure scheme. Okay, now the obvious question is, how often do we need to call this signer oracle? How often does this case occur? And what they showed is that this occurs a logarithmic number of times, and to show that they need this increasing number of sessions. Okay, so Katz, Loss, and Rosenberg have this transformation, and if we look into the efficiency of it, then it scales linearly with the number of interactions n. So over time, this gets less efficient. The communication and the computation cost scales linearly. What we did in our work last year at Crypto was to improve the communication complexity. So we went from a linear dependence on n to a logarithmic one. But we didn't really look into the computational costs of it. And in the same work, we also introduced a scheme, a specific scheme, not a generic transformation, that is called Pikachu. And Pikachu is basically also a boosting kind of thing, but you start from an even weaker primitive, namely a key-only secure blind signature scheme. So in this key-only secure scheme, the malicious user is not allowed to talk to the signer at all. It only gets the key. Okay, and what we did there to get this fully secure is we did the same boosting, but with many parallel instances. So we had many public keys that are independent, and now we do, in every interaction, we do n sessions over k public keys. Okay, and what we could show there is that over the entire run of the experiment, there is at least one instance for which there is no cheat at all. And this means in the reduction, we can look at this instance, embed our challenge public key there, and then because there is no cheat, we never need a signer oracle, so key-only security is sufficient. Okay, so that means we had a scheme last year at Crypto, Pikachu, with 7 rounds. I didn't talk about round complexity yet, but just believe me, it has 7 rounds. It has logarithmic communication and linear computation complexity. And now in this work, we actually improved this. We present Raichu, which is a 2-round scheme. It is stateless, so we got rid of this state for the signer entirely, and that also means the communication and computation is now constant over time. And in addition to this basic blind signature scheme, we also introduced the idea of batching blind signatures to further reduce the communication costs if you want to get many messages signed at once. And we also extend this to the partially blind setting. Okay, so in summary, this world of boosting looks like this now. We have the KLR scheme with linear communication and computation. In the work last year at Crypto, we improved the communication, and now we got rid of the counter or the state entirely. Okay, so for the rest, I want to talk a bit about the techniques that we use. How can we achieve this actually at a very high level? Okay, so as I said, there is this Pikachu scheme, and the idea is that there's one instance over the entire experiment where there's no cheat, so we don't need a signer oracle for that instance. Now, the first thing we could try is, what if we remove the counter and just say the number of sessions is constant all the time? So what do? Let's say we take 4 sessions, and in every interaction, for every instance that we do, we have 4 sessions. Okay, this situation looks something like this. Now we can no longer show that there's one instance over the entire experiment with no cheats. But what we can argue is that for every interaction, there is one instance with no cheat. Okay, so the situation looks a bit different now. It looks like this. In every interaction, you have potentially a different instance where there is no cheat. Okay, so how can we use this? Well, if we just have our keys like this, it doesn't really help us because we have to decide in the beginning where to embed our challenge key, and as long as there's one cheat, we are screwed. So the idea is now to have the public keys different in every interaction. So how does that look like? We have the signer and the user. They do some interaction, and then at some point, the signer will decide what keys to use. So the signer will send this set of K keys to the user. And then they interact in this parallel instance cut and choose as in Pikachu. Okay, so why is this helpful? Well, let's say we want to reduce the security of this to the security of the underlying key-only secure scheme. Then what we get as input is a challenge public key. And now in every interaction, we use some tricks to learn this instance I star for which in this interaction there will be no cheat. Then in this instance, we embed our challenge key. And the implication of this is that now for this instance, there's no cheat, so we can simulate without the secret key. For all the other instances, we have a secret key, so we can also simulate. Okay, so that tells us that with this strategy, we can simulate the signer. But if you look at this for a while, you see there's an obvious problem. If we send public keys, fresh public keys in every interaction, and it's not clear what is the relation of these public keys to the actual public key of the scheme, right? So right now the interaction looks like it is independent, so how can this be unforgeable? And to sort of solve this problem, that's the problem. So the problem is how can we relate these public keys to the long-term key, and technically this shows up when we want to take the forgery of the adversary and get a forgery of our challenge key. Okay, so the idea that we had here is we do the same thing, but we have now a relation between these public keys that you send in every interaction and the long-term key. And the relation is basically a sharing. It's a very simple sharing of the public key, and by appropriately defining this sharing, you can still use the same embedding strategy. You can make sure that for all but one of these keys, you know the secret key. So I don't want to talk more about that. Let me instead summarize what we have done in this work and what we have seen in the talk. So we have this new blind signature scheme, Raichu. I didn't talk about assumptions yet, so let me tell you, this is from the CDH assumption in the pairing setting. It has 2 rounds, so it's round optimal. It is stateless, in contrast to the previous works, and it has a constant communication and computation complexity. And we also implemented this and looked at the concrete efficiency. So there are different ways to set the parameters. You have different trade-offs. You can, for example, focus more on the signature size and improve that, or you can focus on the communication size depending on how you set, for example, the number of instances that we have. And you see the signature sizes, communication sizes, and also the running times are reasonably efficient. So I want to conclude with an open problem that I would like to mention, and I hope that at some point someone can solve it. So you see this scheme, it's efficient, but it still uses pairings. And an obvious question is, can you even improve it more by getting rid of the pairings? So the previous works, they all had sort of generic transformations. We have a specific scheme. So the question is, can you have a pairing-free construction or even make this approach that we have somewhat generic such that you can instantiate it without pairings? So if you have any ideas about this problem, so feel free to talk to me. I'm happy to talk about it. And yeah, with that, I thank you for your attention and happy to answer questions.
Thanks a lot for your talk, Benedict. Are there any questions for a speaker? So the obvious question regarding the open problem from my side would be, so what's the problem?
Okay, so
removing the pairings.
Yeah. So we tried it. Actually, if you take Pikachu and you can implement it based on Schnorr, basically. then it will not be efficient, but at least it works, right? So you lose the aggregation feature, which is sort of bad for efficiency, but it still works. For write-through, we have this sharing of the public key. So what you get in the end as a forgery is basically an arbitrary sharing that the adversary came up with of your challenge public key and some Schnorr signatures for that. We don't really know what to do with them. If we have BLS signatures, then they are already aggregated, and sort of the algebraic structure helps you to use that. But for Schnorr, there's a random oracle, and
I see.
it's not really clear what to do with these signatures.
Okay, thanks a lot.
Yeah.
Good. If there are no further questions, then I guess we are done. So I wish all of you nice remaining Eurocrypts. Have a safe trip back home, and let's thank all the speakers again.